Find Q and R for the following pair of positive integers a and b satisfying a is equal to bq plus r. Here a is given 13 and b is given 3. Now we can write this equation as a equal to bq plus r. A is 13, that is equal to b is 3, and into we can write 13 is b 3 into 4 12 plus remainder is 1. Now it is in the form of a equal to bq plus r. Here a equal to 13 and b is equal to 3, q equal to 4 and r equal to 1. Next 80 is equal to b, a equal to 80 and b equal to 8. There a is equal to 80 is equal to b is 8 into 10 plus 0. It is in the form of a equal to bq plus r, where a is 80 and b is equal to 8, q is equal to 10, r equal to 0. Let us take 125, a equal to 125, b equal to 5. 125 is equal to 5 into 5 to the and 5 5 plus 0. 5 into 25, 125 plus 0. It is compare with bq plus r. Then let a equal to 125 and b is equal to 5 and q is equal to 25, r equal to 0. A equal to 132, b equal to 11. There a equal to 132, b equal to 11. So 132 is equal to 11 into 12 plus 0. A is equal to b q plus r. A is 132, a equal to 132, b is equal to 11, q is equal to 12 and r equal to 0. Find the HCF of the following by using Euclid algorithm 50 and 70. For given two positive integers a is greater than b, there exists unique pair of integers q and r satisfying a equal to bq plus r, where 0 is less than or equal to r less than b. So we can write this: a is greater than b, that means a is 70. 70 is greater than 50. So we should take a equal to 70. 70 is equal to b is 50 and into 1 plus 20. 50 plus 20 is 70. So now 70 is equal to 50 into 1 plus 20. The remainder is or is not equal to 0. So you continue the same, and this equal to, again continue the same. 50 is equal to 20 into 2 plus remainder is 10, and again you write this 20 is equal to 10 into 2 plus 0. Now A is equal to BQ plus R, and R is 0. Here R is 0. So R equal to 0. So then B is the HCF of this 70 and 50. Therefore, here the remainder is 0. Then the 10 is the HCF of 70 and 50. Find HCF of 96 and 72. 96 and 72. 96 is A, 72 is B. 96 is greater than 72. So A equal to BQ plus R. 96 is equal to 72 into 1 time plus 4 and 2, 24. So again the remainder is not 0. We should continue the same. 72 is equal to 24 into 3 times plus remainder is 0. So now it is in the form of A equal to BQ plus R. A is equal to BQ plus R. R is here, R is 0, A is 72, and B equal to 24, R is 0. When the remainder is 0, the B is the HCF of these two numbers. Then 24 is the HCF of 96 and 72. Find the HCF of 300 and 550. 550 is equal to 300 into 1 plus 250. Remainder is not 0, still continue up to remainder 0. 300 is equal to 250 into 1 plus 50. The remainder is again not 0. So 250 is equal to 50 into 5 plus 0. The remainder is 0. Now the HCF is the B value, that is 50. Find the HCF of 1860 and 2015. 2015 is greater than the value 1860. So A equal to 2015 and B equal to 1860. 2015 is equal to 1860 into 1 plus 155, and the remainder is not 0. Then 1860 is equal to again 155 into 12 times, and is 1860 plus remainder is 0. Now the remainder, when the remainder is 0, the B is the highest common factor of these two numbers. HCF equal to 155. Division algorithm, the theorem. Given positive integers A and B, there exist unique pair of whole numbers Q and R, satisfying that A equal to BQ plus R, where R is 0 less than R equal to R less than B. What is the nature of Q and R? Q is always greater than 0. Q is always greater than 0, and r lies in between, r lies between 0 and less than b, r lies between 0 and b, q is always greater than 0. Can you find the HCF of 1.2 and 0.12 by using Euclid division algorithm? Justify your answer. No, no, it is not possible to find HCF of 1.2 and 0.12 by using Euclid division algorithm, because Euclid division algorithm is used to, it is applicable for only positive integers, but here 1.2 and 0.12 are not integers, these are decimal numbers, so it is not applicable for this Euclid division algorithm. Show that every positive even integer is of the form 2q, and that every positive odd integer is of the form 2q plus 1, where q is some integer. Now let a be any positive integer. Then here 2q is given, that means 2q means b equal to 2, then the division algorithm is a is equal to 2q plus r, but r is lies between 0 less than or equal to r less than b. Here b equal to 2 is given, then 0 less than or less than 2. That means r equal to, we can take 0, 1, 0 and 1. Then a is equal to 2q plus 0. That means, so that is a is equal to 2q. Q is greater than 0, and again r equal to 1, then a is equal to 2q plus 1. Now this is, therefore if a is of the form 2q, that means q is equal to 1 2 3 4, any value, that a is even integer. If we substitute the q equal to 1 2 3 4, 1 means 2 into 1, 2 into q equal to 2, 2 into 2 4, 2 4 6, like that we will get a values. All these are even integers. If you take q equal to 1, in this a is equal to 2q plus 1, we will get 2 into 1 plus 1, that equal to 3. And if q equal to 2, 2 into 2, that equal plus 1, that is 5. That is 3, 5, 7, we will get a equal to 2q plus 1. So it is odd integer and 2q is even integer. Therefore, a positive integer can be either even or odd. For this, a equal to 2q is even and a equal to 2q plus 1. So even or odd. Therefore, any positive odd integer is in the form of 2q plus 1, and 2q a is in the form of 2q, and then it is an even integer. Show that every positive odd integer is of the form 4q plus 1 or 4q plus 3, where q is some integers. That means let a be any positive odd integer, a be any positive odd integer, and here is b equal to 4 given. So b equal to 4q plus 1, that means b is 4. Now we can write this equation uh, division algorithm for this, applying this a equal to 4q plus r, 4q plus r, where q is greater than 0, and r is lies between less than or equal to 0 and less than b. This is our values. B means 4 is given 4. So then we can write r equal to 0 and r equal to 1, r equal to 2, r equal to 3. Less than 4 means r equal to 3. So now apply in this equation a equal to 4q plus 0 if r equal to 0, and this is a equal to 4q, the first one. The second one, a is equal to 4q plus 1, this is number 2 if you take r equal to 1, and again a is equal to 4q plus 2, uh, here a is equal to 2 into 2q plus 1, 2 into 2q plus 1, this is number 3. The third one is a is equal to 4q plus 3, 4q plus 3, this is number 4. Now look at, observe these all. The first one is 4q, and second one is 4q plus 1, and third one is 2 into 2q plus 1, and fourth one is 4q plus 3. That means we can write this 4q plus 3 is 4 2 into 2q plus 1 plus 1, 2 into 2q plus 1 plus 1, because 2 into 1 1, 2 and 1 is there, 3 is 3, we can write in. Okay, we wait for this. A is equal to 4q plus 3, that 3 we can write 4q plus 2 plus 1. So take common for this, 2q plus 1 plus 1. So now this is the fourth one, and the first one is 2 into 2q, here is 2 into 2q. Also we can write this, the first equation 4 means 2 into 2q, 2 into 2q. So second one is 2 into 2q plus 1, and here is 2 into 2q plus 1. So observe this, and here 4q or 4q plus 1, 4q or 4q plus 1, and 4q plus 2, 4q plus 3, where q is as a coefficient. However, since a is odd, a cannot be 4q, a cannot be 4q. To add this if a equal to 4q, it is not odd number, it is always even number. So which is equal to, we can write 2 into 2q. That means 2q is a number, and multiplying with 2 we will get even number. So also in the same way, 4q plus 2 is, uh, we can write 2 into 2q plus 1. 2q plus 1 is a number, and multiplying with 2 we will get even numbers. This first one and the third one we will get even numbers. So it is divisible by 2. It is also divisible by 2. It is also divisible by 2. Then these two are 1 and 3 are even numbers, and 2, now observe here, 4q means 2 into 2q plus 1. 2 into 2q is even, plus 1 is odd number, and here is also 2 into a number multiplying with a number plus 1 is odd number. Now observe here, a equal to 4q mean a equal to 2 into 2q, and here a is equal to 4q plus 1 means 2 into 2q plus 1. Here is a equal to 4q plus 2 means 2 into 2q plus 1. Here is a is equal to 4q plus 3 means 2 into 2q plus 1 plus 1. So 2q equal to, just here is 2q is equal to k, then 2k, and here is a equal to 2k plus 1. Now here 2q plus 1 equal to k, then m, this is 2m, and a is equal to, this is m plus 1. Now observe it, this is odd number because a is divides here, it divides by 2, and this it also divides by 2, but it is not divides, it is not divides. So this first one, 4q comma 4q plus 2 are even numbers, even, and 4q plus 1 and 4q plus 3 are odd. So that every positive odd integer of the form 4q plus 1 and 4q plus 3. Use Euclid algorithm to find the HCF of 900 and 270. Here a equal to 900 and b is 270. 900 is equal to 900 is equal to 270 into 3 times plus remaining is 270 into 3 times plus 270 into 3 is 301, and 2 is 810, and 900 minus 810, the remainder is 90. Here is 90. The remainder is not equal to 0. Again take next step, continue the same. 270 is equal to 90 into 3 times plus 0. The remainder is 0. Now this B is become HCF. The HCF and 90 is the HCF of 900 and 270. Find the HCF of 196 and 38,220. Here A is 38,220 because it's greater than 196. So write here 38,220 is equal to 196 into divide. If you divide this 38,220, we will get 195. 195 into 196 is 38,220. The remainder is 0. Directly it is 0. So 196 is the HCF of these two numbers. Therefore, HCF is equal to 196. Find the HCF of 1651 and 2032. Here A is 2032. So we can write this equal to 2032 is equal to 1651 1 times plus 2032 minus 1651, that equal to 1 and 8 and 3. 381 is remainder. So 1 time. So this equal to, remainder is not equal to 0. And continue the same again. 1651 is equal to 381 into 4 times, because 1600 is there. 381 means 400, 4 times, like 4 times is 4 ones are 4, 4 eights are 32, and 4th is a 12, 3, 15. So that remainder is minus, so 127. Again, this continue the same again. 381 is equal to 127 into 3 times. 3 times is 3 sevens are 21, 2, 3 twos are 6, 2 8, 3 ones are 3, 381, 0. Now the remainder is 0. Then HCF of 1651 and 2031 is 127. Use division algorithm to show that any positive add integer is of the form 6q plus 1, 6q plus 3 and 6q plus 5, where q is some integer. Let a be an add positive integer. Let a be an positive integer. Let us now apply the division algorithm with a and where b is equal to 6 is given. Then that equation is b is equal to 6 q plus r, but r lies between 0 less than or equal to or less than 6. That means r is equal to, we will get the values 0, 1, 2, 3, 4 and 5. Now let a can be written as a equal to 6q plus 0. That means a equal to 6q. This is number 1. and a is equal to 6q plus 1. This is number 2, and a is equal to 6q plus 2. This is 2 into 3q plus 1. This is number 3, and a is equal to 6q plus 3. This is number 4, and a is equal to 6q plus 4. That means 2 into 3q plus 2. This is number 5. This is 4, and a is equal to 6q plus 5. This is number 6. Now observe this. The first one is even number, a equal to 6q. The first one is even number, and the second one is 6q means 2 into 3q plus 1. So it is odd number, and the q is the coefficient is here. And the third one is 2 into 3q plus 1. It's a number 2 multiplied, so it is even number. Fourth one is also 6q plus 3. Plus 3 means it is odd number. And the fifth one is 2 into some number. It is even number. And the sixth one is also odd number. From all these, we can write odd integers are 6q. Odd integers are 6q plus 1 and 6q plus 3 and 6q plus 5. Six q plus 5. These are the odd integers, or in the form of 6q plus 1, 6q plus 3 and 6q plus 5. Use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. Now let a be positive integer. Let a be positive integer. Then from Euclidean lemma is that a equal to bq plus r. Now consider here the b is 3. Consider that b equal to 3. Then r is lies between 0 less than or equal to r less than b. P means 3. Then our values are, and it means remainder will be that our values 0 and 1, 2, because less than 3 means 0, 1, 2. We will get from this. Now so a equal to bq plus r. A is an integer, positive integer. Now a equal to bq plus r, but here asked the square of any positive integer. Square means a square. Now a square is equal to, we can write bq plus r. r equal r whole square. We know that b value also. Yeah, b value is 3 is there. So 3b 3q plus r whole square. This is the positive integer. The square of positive integer is a square is equal to, we can write 3q plus r whole square. But is it in the form of a plus b whole square? Now a square is 9 square, 9q square, sorry, 9q square plus 2ab means 2 into 3q and r plus r square. Then this equal to 9q square plus 6q r plus r square. This equal to, here is the 3 is common to this. I am taking 3 is common. 3q square plus 3 2qr plus r square. This is a square is equal to 3 into 3q square plus 2qr plus r square. But here 3q square plus 2qr equal to, we can write this equal to 3p plus r square, because p is equal to 3q square plus 2qr is a number. Now substitute the values in the equation. Now here is 0 less than or equal to r less than 3. That means r equal to 0, 1, 2. Now substitute the value r equal to 0 in this equation. A square is equal to 3p plus 0. Then a square is equal to 3p. And if you substitute the value r equal to 1, then r is equal to 1, then a square is equal to 3p plus 1 square, 3p plus 1 square, that a square is equal to 3p plus 1. This is number 1, this is number 2. And substitute the value r is equal to 2, then a square is equal to 3p plus 2 square. This equal to 3p plus 4. Plus 4 means what? We can write 3 plus 1 this is. So 3p plus 3p plus 1. 3 plus 1. So 3 is 0 because remainder should not greater than b. So 3 is 0 or 3 is common and 3p plus 1 we can write. So this is number 3. Now look at here. 1 is 3p and 2 is 3p plus 1 and yes, the third one is also 3p plus 1. Therefore the square of any positive integer is of the form 3p or 3p plus 1. Here is 3p or 3p plus 1. This is 3p or 3p plus 1, 3p plus 1. 0, 1, 2. If you substitute the 0, that is 3p. If you substitute 1, 3p plus 1. If you substitute 2, also 3p plus 1. Use the division algorithm to show that the cube of any positive integer is of the form 9m, 9m plus 1 or 9m plus 8. Now let a be a positive integer. Then from the Euclidean lemma, we know that it is a positive integer. Let a be any positive integer. Now from that uh, Euclidean lemma, we can write what a is equal to bq plus r, a equal to bq plus r. Here is given 9m, 9m plus 1, 9m plus 8. That means 9 is the value of b. B is equal to 9 is given. Now substitute this in the equation. A is equal to 9q plus r, where r, the r values are, r is lies between 0 and less than b. B means 9. So then the values of r is 0 to 9. 0 to 9 means r equal to, we can take 0, 1, 2, 3, 4, 5, 6, 7, 8 less than 9. So we can write these are the positive integers. We can get all these, that is a equal to, if you substitute the 0, 9q, and if you substitute the 1, a equal to 9q plus 1. If you substitute r equal to 2, a equal to 9q plus 2, and if you substitute a equal to 3, 9q plus 3, and a equal to 9q plus 4, and so a equal to 9q plus 8. These are the integers we will get from the equation. Now a cube is equal to 9 cube, 9 cube and q cube, 9 cube, q cube plus 3, 9 square, 3 into 9 square into q or r 9, 9 square into q square into r square, r plus 3 into 9 into qr plus r cube is equal to, a cube is equal to, 9 is common to all, so take common 9 of 9 square q cube plus 3 into 9 q square r plus 9 common here, 3 qr, So it's common over and plus r cube. Okay, and that equal to a cube is equal to 9 into, there is a value, this is the value, is take, but what is that? The value is q 9 square q cube plus 3 into 9, 27 q square r plus 3 q r, this equal to, so that is p. Now we can write this equation, a cube is equal to again 9p plus r cube, 9p plus r cube. Now a cube is equal to 9p plus r cube. This is the cube of a positive integer, positive integer form. Now we can say the r values are, we know that 0, 1, 2, 3, 4. Substitute in this equation, and a cube is equal to, if a equal to 9q plus r and a cube is equal to 9p plus r cube. R values we should submit here. You should submit here 9p plus 0 if r equal to 0, and that is 9p. A cube is equal to 9p. This is number 1. And the second one, r equal to 1. If you substitute r equal to 1, a cube is equal to 9p plus 1 cube. This equal to 9p plus 1. This is equation number 2. Now if you start the value r equal to 2 and a cube is equal to 9p plus 2 cube is equal to 9p plus 8. This is number 3. If you substitute the value r equal to 3, then a cube is equal to 9p plus 3 cube, that is equal to a cube, that equal to 9p plus 3 cube means it's a 0 because it's a factor of 9. It's a multiple of 9, 27 is, so it is 0. Then this equal to 9p. This is number 4. Okay. Now a equal to, substitute the value 4. R equal to 4. Then a cube is equal to 9p plus 4 cube. 4 cube means 64. We can write a cube is equal to 9p plus 4 4 the 16 4 the 64, that equal to 9p plus 64 means a multiple of 69 is 63 plus 1. 63 is a multiple of 9, so it is 0. Then a cube is equal to 9p plus 1. This is number 5. And again, if you substitute the value r equal to 5, and then a cube is equal to 9p plus 5 cube, So this equal to 9p plus 5 cube is 125. 125. Then 9 multiple is, what is the 9 multiple of 125 is 117. 117 plus 8. So we can write this. This is the multiple of 9, so it is 0. 9p plus 8. This is number 6th one. And like a equal or equal to 6. If you substitute r equal to 6, a cube is equal to 9p plus 6 cube. This equal to 9p plus 6 cube. 36. 6 into 36 into 6. 6 cube is 216. It is a multiple of 9. So that is 9p plus 0. Therefore, a cube is equal to 9p. This is equation number 7. Of a cube is equal, if r equal to 7, a cube is equal to 9p plus 7 cube. 7 cube is equal to, then a cube is equal to 9p plus 343, and a cube is equal to 9p plus 342 is a multiple of 9, and that is 0, and remainder is 1. So this is number 7th one. The last one is r equal to 8, and a cube is equal to 9p plus 8 cube, that equal to 9p plus 8 cube, 64. 8 cube is 512. So we can 9p plus 504 is multiple of 9 and plus again 8. So this is 0. We can write 9p plus 8. This is number 9th one. From all these, we can understand that in the beginning, the first one is 9p. Number 1 is 9p, and the number 2 is 9p plus 1, and number 3 is 9p plus 8, and again number 4 is 9p number, and this one 7th one is also 9p plus 1, and the last one is 9p plus 8, and this is 9p and 9p plus 8, and this is 9p plus 1. So we are getting a cube is equal to 1 is 9p, and another one is a cube is equal to 9p plus 1, and a cube is equal to 9p plus 8. So if a positive integer, the cube of any positive integer is of the form is 9p and 9p plus 1, 9p plus 8. That means 9m, 9m plus 1, 9m plus 8. So that one and only one out of n comma n plus 2 or n plus 4 is divisible by 3, where n is any positive integer. Now let us take n be any positive integer, and let n be any positive integer. Then from Euclidean's lemma, we can write n is equal to bq plus r. But here is divisible by 3, that means b equal to 3. B equal to 3. Now substitute this in this equation. 3q plus r. The r values are lies between less than 3 plus b is 3. Then now 0, r values are 0, r equal to 0 and 1 and 2. This means the possible values of r is 0, 1 and 2. Now r equal to 0, substitute here n. We have 3 values are there, n plus 2, n plus 4. 3 values are there, n plus 2, n plus 4. Now substitute in this equation. First n is equal to 3q plus 0, and the second one is n is equal to 3q plus 1, and the third one is 3q plus 2. I will write. So n is equal to 3q plus 0. That means n equal to 3q. It is divisible by 3 because 3 into it is divisible by 3. The second one is n is equal to 3q plus 1. It is not divisible by 3. And the next one is r equal to 3, n is equal to 2, 3q plus 2, r equal to 2. Substitute the value 2. This is also not divisible by 3. The first one is divisible by 3, 3q, and second one and third one is not divisible by 3. For n value, now take n plus 1 value. Now take n plus 2 value. For n plus 2, then a is n, so n is equal to 3q plus r equal to 0. Then n plus 2 value, that means n plus 2 is equal to 3q plus 2. It is 3q and n equal to 3q and plus 2. It is not divisible by 3. So n plus 2, and the next value r equal to 1. N is equal to 3q plus 1 and n plus 2 is equal to 3q plus 1 plus 2 is equal to 3q plus 3. If you take common of 3, q plus 1, it is divisible by 3. It is divisible by 3, n plus 2. And the next one is r equal to 3, n equal to 3q plus r, and r equal to 3. then n is equal to 3q plus, sorry, 2r equal to 2, 3q plus 2. Now n plus 2, we have to find this. N plus 2 is equal to 3q plus 2 plus 2 is equal to 3q plus 4. It is not divisible by, it is not divisible by 3. So next one is n plus 4. Now n is equal to 3q plus r, where n equal to 3q plus 0, then n plus 4 is equal to 3q plus 4. It is not divisible by. Divisible by 3. So then n r equal to 1, n plus 4 is equal to 3q plus 4 plus 1, that is 5. It is also not divisible. Divisible by 3. The next one is n equal to n plus 4 is equal to n or equal to 2. That means 3q plus 6. 3 is common. Q plus 2. So it is divisible by, it is divisible by 3. Now in the case 1, only 1 is there, and in case 2 is also 1 is there, and 3 is also 1 is there. For this n plus 4 case, only 1 is divisible, and n plus 2 is also 1 is divisible, and n is also 1, only 1 is divisible.